We're beginning our unit on work, and it's important to understand that in physics, work means something that it does in day-to-day life. In day-to-day life, we think of work as being a task or a job we have to complete. But in physics, we define work as when a force causes an object to move through some distance. Okay, so work is done when a force acts on an object and the object moves through a distance. And in order for that to count as work, the force and the motion have to be in the same direction, or at least some component of the force and the motion have to be in the same direction. Now, work is a scalar quantity, which means it doesn't include direction. You can't say work to the right. It's either work or it's not. But there is a little kind of disclaimer on that. We calculate work by taking the magnitude of force times the magnitude of a distance times the cosine of the angle between those two things. So I said magnitude, which basically means the absolute value. So we're not going to use negative work or positive work. We're not going to use negative or positive distance. We're just going to assume absolute values, everything's positive. But then we do have times the cosine between them. And cosine actually is a function that has a range of -1 to 1. Remember, a cosine curve starts at 1 and goes through an entire cycle in 360 degrees. At 180 degrees, it's at -1. Okay? At 90 degrees, it's at 0. At 270 degrees, it's at 0. And at 0 degrees, it's at 1. Which means we have a possibility of negative work. And what that means is we'd be at 180 degrees between the force and the displacement. So negative work is when the force and displacement are in opposite directions. Positive work is when the motion and the force are in the same direction. And if they're at right angles to each other, where the angle's 90 degrees, then no work is done because the cosine of 90 is 0. One last thing here on work, the units of work. We calculate work by taking a force measured in newtons times a distance measured in meters. An angle has no dimension. That gives us a unit of a newton times a meter, which is called a joule. The abbreviation for joule is capital J. It's spelled like that, Joules. So joules of work is a joule of work is the amount of work done when a 1 Newton force moves a distance through 1 meter. Now let's go ahead and take a look at an example and see if we can use this definition. Now I'm going to start with an example that has a lot going on, but none of it's going to be super tricky. So I have the ground sitting here, and let's go ahead and put a box on the ground. And keep the math easy, 10 kilograms. We're going to apply a force this way, Fa, against a frictional force this way, Fk, and we're going to move the box 5 meters to the right. So we're going to have motion this way. And coefficient of friction equals 0.3. And let's see, the velocity here is constant. I don't care what it is, but I do care that it's constant. So what I want to know is the work friction does. I want to know the work that the applied force does, and any other things that are going on in here. Okay, so the first thing I'm going to look at is I want to know, well, if friction is doing work, I need to know how big friction is. And in order to get friction, I know that Fk is equal to the normal force times the coefficient of friction. Well, that means I actually have these other two forces, right? Gravity and the normal force. We also have to consider, are they doing any work? But before we get there, let's just get our frictional force. So Fk equals the normal force times the coefficient of friction, but I don't have the normal force. But I do know that the net force in the y direction, which is Fn minus Fg, is 0 because this is sliding along the ground. It's not moving up or down, not accelerating up or down. So Fn is equal to the opposite of Fg, which is mass times the acceleration due to gravity, 9.8. And I know the mass is 10, so the normal force equals the force due to gravity. Both of these are 98 newtons. So Fg equals 98 newtons. Fn equals 98 newtons. Now I can find Fk. Coefficient of friction is 0.3. 3 times 8 is 24. 3 times 9 is 27. Carry that, and I got 29.4 newtons of friction. So Fk is 29.4 newtons. Now, same reason, because we're moving at a constant velocity, the net force in x is also 0. So if Fk is 29.4 newtons, then Fa is also 29.4 newtons. They're just in opposite directions. So now when I want to find the work done by friction, I'm going to take 29.4 newtons times the distance that it moves, 5 meters, times the cosine of the angle between those. But remember, friction is pulling this way, and the box is moving this way. That's an angle of 180 degrees. So what I have is 29.4 times 5. 5 times 4 is 20. 5 times 9 is 45. 7. 5 times 2 is 10. So 147.0 Newton meters times the cosine of 180 degrees. Well, that is -1. So I have a negative 147 joules, Newton meter is a joule, of work. So friction does negative 147 joules of work. How much force did the applied force do? Well, if we go to that one, FA is 29.4 times 5, and we're going to get the exact same thing, except this time it's times the cosine of 0, because this time the force is this direction, the motion is this direction. There is no angle between those, they're parallel lines. So this is 29.4 times 5, which is 147.0 Newton meters, times 1, which gets us 147 joules of work. So these two things exactly undo each other. We did 147 positive joules of work against friction, which did 147 joules of negative work. Okay. What about normal force and gravity? Did they do any work? Turns out no. Why didn't they do any work? Even though there's a force and there's motion, we have gravity acting up, or sorry, the normal force acting up 98 newtons. We have our motion this way, 5 meters. This angle between them is 90 degrees. And remember, 98 times 5 times the cosine of 90 is 0. So gravity and the normal force, neither one of them do any work on this thing because they're at right angles to each other. Last case to look at would be like the case if we have a similar thing, but instead of pulling straight to the right on it, we pull up and right on it. So if this is 20 newtons and this is 10 kilograms and this is 60 degrees, but we're only dragging it across the floor that way, how much work are we actually doing on this box? Well, if I want to know just the work of my applied force, there could be friction doing some other work, but we're just going to look at my applied force in this one. Well, work is force times distance times the cosine of the angle between them, and in this case, if I'm moving this way and pulling this way, that would be 20 times whatever my change in position is, however far I pull it, times the cosine of 60 degrees. Now you'll notice 20 cosine 60 degrees is just the x component of that force. So all we did by doing that is found the component of the force that acts in the same direction as the motion. So it's just a vector component problem.